So deriving Kb from Ka. The key to answering this kind of question is knowing that there's a relationship between the two, and it's based on the ionic product for water, Kw. So whenever you multiply Ka for an acid times Kb for its conjugate base, that will equal the ionic product for water, which is 1 times 10 to the power of minus 14. So you can always calculate one from the other. I made a bit of a pig's ear typing that. There we go. It's trouble when you don't look at your fingers. Okay, so there's an inverse relationship. The bigger Ka is, the stronger the acid, right? The more that equilibrium lies to the right, then the weaker its conjugate base. So the smaller the value of Kb. And vice versa. If something is a stronger base, the weaker its Ka value of its conjugate acid is going to be. Okay, so just remember the Bronsted-Lowry definition of acids and bases. Acid is a proton donor, and the base is a proton acceptor. So to work out the formula of a conjugate, all you have to do is, if you have an acid and you want to know the formula of its conjugate base, the conjugate base is going to be whatever is left behind, right? So if your acid is Ha, then its conjugate base is going to be the anion component, A minus, what is left behind after it has donated its proton. Similarly, if you have a base and it accepts a proton, what is the formula of the base going to be? Well, it's whatever the formula of the base was, and its conjugate acid will be B with a proton stuck to it, right? It's just going to accept a proton. So you can use this to write the formulas for the conjugate base of a weak acid or a conjugate acid of a weak base, as you like. All right, so let's go ahead and do that, I guess. So right, the conjugate base of HCH3CO2, we don't know what it is, you know, it's acetic acid, right? I'm sure it's overused by that. So it's just going to lose its proton. So it's going to lose an H plus. So we can just write CH3, if I could get my cursor anyway, CH3CO2, and of course that will now have a -1 charge, okay? Because it has lost a proton, which is an H plus. Okay, so what about the formula of the conjugate acid of this base? That's pyridine, right? So this base is going to accept a proton, so we're going to add an H plus to it. So that will be C5H5 and then add H plus, so NH plus. C5H5NH plus. That's all we have to worry about with that. And NH3, if you add a proton to it, add an H plus, it'll be NH4 plus. So then all we have to do is use our expression that relates Ka, Kb, and Kw to work out what Kb and Ka is respectively. Okay, so for my acetic acid, the acetate ion, my Kb for the acetate ion is going to be Kw divided by Ka. That's just simply rearranging the equation. So Kb, and I'll put in brackets for my acetate ion just to be absolutely clear, is going to be Kw, which is always 1 times 10 to the power of -14, divided by Ka for my acetic acid, which was given to me in the question, is 1.8 times 10 to the power of -5. Stick that in my calculator, and I should get 5.6 times 10 to the power of -10. Okay, and that makes sense. Think of that inverse relationship. Okay, that the stronger the acid, the weaker the base. So we're in the order of magnitude of 10 to the power of -5 for the strength of our acetic acid. So our acetate ion should be a pretty weak base in comparison. So I'm not going to be able to fit that in the box, but you guys go ahead. All right, so the Ka for my conjugate acid of pyridine. So Ka is going to be Kw divided by Kb. So of course that would be Kb for my pyridine, my C5H5N. So Ka for C5H5NH plus is going to be 1 times 10 to the power of -14, the value of Kw, that is always going to be the same, divided by my Kb for my pyridine, which is given to me as 1.7 times 10 to the power of -9. So that's a relatively small value for Kb, 10 to the power of -9. So I'm expecting a larger value for Ka for my conjugate acid. And sure enough, that shakes out to be 5.9 times 10 to the power of -6. Okay. All right. And then lastly, Ka for my ammonium cation. So again, that would be Kw over Kb. So NH4 plus. It's going to be Kw, so 1.00 times 10 to the power of -14 divided by Kb for ammonia, which is 1.8 times 10 to the power of -5. Okay, so 1.8 times 10 to the power of -5, I'm going to expect a much smaller value for the value of Ka for my ammonium. So relatively, ammonia, although it's still a weak base, it's going to be a stronger base than ammonium is strengthens the acid, right? And that comes out to be 5.6 times 10 to the power of -10. So these numbers really show you that inverse relationship for a weak acid in its conjugate base or a weak base in its conjugate acid. As the strength of one goes up, the strength of the other goes down.